Hello everyone. Today we're going to continue to talk about Euclidean geometry, which basically just try to study more about lines and plane. So yesterday videos we talked about lines and how to rewrite it into what we call standard form of a line. So the important part about it is to understand that standard form of a line is basically allow us to identify the perpendicular vector. And as a matter of fact, you cannot write the standard form of a line without the perpendicular vector. It just doesn't work because the perpendicular vector defines the coefficient for the variables and also define what the equation is equal to. Now, um, now that we know the standard form and also know how to use the perpendicular vector to describe it, now some of the interesting things I want to point out about lines would be the following. Probably most basic question they want to find out is if we have two lines, can we determine if they are parallel or perpendicular using the perpendicular vector? As a matter of fact, you find out that using the perpendicular vector to describe two lines that are parallel or perpendicular is exactly the same way as if you were to use two direction vector of the line. So here's the concept right here. Two lines are parallel to each other if this is true. If their perpendicular vector if the perpendicular vectors are multiples of each other. So that's the same exact concept as if you were doing the direction vector of the line. If they're multiple, then they have to be parallel. And here you're using the simple concept in geometry, which state that if you have two lines that are perpendicular to the same line, they must be parallel to each other. That's basically what the idea is here. Now, with the perpendicular vector, we can also now identify if two lines perpendicular to each other also, and that would be this. Now here is very interesting, very important here. Two intersecting lines are perpendicular to each other if the dot product between their perpendicular vector is 0. Now the important word here is this word right here. Okay, maybe I can do a little bit better. So the important word is this word right here, intersecting. The problem is the following. Normally, that's not an important word because if you know the directions are perpendicular, then they should intercept, right? Well, that's only true in R2. In R3 or higher, it actually would not be the case. Okay? So therefore, when you talk about perpendicular, the definition of perpendicular lines are two lines that intercept and form right angle. So students often forget that it has to be intersecting. And as I say, in R2, that's usually not a problem because if the direction are perpendicular or if the perpendicular director are perpendicular, then in R2, they must intercept. And therefore, it's kind of given if that's the case. Just in R3 or higher, when you try to figure out where two lines are perpendicular to each other, and notice at those instances, you have to do in parametric form, then you also have to make sure that these two lines are not skewered, because if they're skewered, they could have perpendicular direction, but they're not perpendicular to each other because they don't intercept each other. So therefore, it's important to realize that two lines are perpendicular not just because their direction, the dot product of the direction or the dot product of the perpendicular vectors is 0, but also require that they have a point of intersection in order for that to work. You will be asked about perpendicular lines on your test, and you can kind of assume that the test question is very likely to not be in R2, because I just point out to all of you that if you have two lines in R3, even if their direction vector are perpendicular to each other, you can conclude that the two lines are indeed perpendicular unless they intercept. Since I mentioned this concept to you and pointed out that is important, you can pretty much guarantee that I will ask you on your test. So make sure you be aware of that. Now, of course, with equation in standard form is not that big of a deal, because why? Remember, we can only form an equation or line in standard form in R2. So therefore, if you have an equation of a line, then it has to be in R2. And therefore, if you look at if they're perpendicular direction already, then they must intercept because they're not parallel. But once you get to higher dimension, then you have to pay attention to the fact that lines might not intercept each other. Now, I'll give you a very simple example. So a question would be something like this that I can ask you. And let's do one that's in R2 first, so that's easy. Let's say, given two lines, let's say vector x is equal to t negative 2, 1 plus 1, 5, and let's say vector x is equal to t 4, negative 2 plus 7, 4. I'm going to ask you to, let's rewrite them into standard form. That's A. And then B, are these two lines distinct? So that means, are they different lines? Are they parallel? Are they perpendicular? Are they intersecting? Now, because this is in R2, some of these words are mutually exclusive, meaning that if they are parallel, they cannot be perpendicular. Okay? If they're distinct, then they might be intersecting if they're not parallel. But if they are parallel and distinct, then they will not be intersecting. So there are definitely some exclusion and some mutually exclusive word here that if one happens, the other one cannot happen. So it makes the problem a lot easier. And obviously, I'm trying to do this just to illustrate the concept for you. And eventually, we'll probably go talk more about what happened if it's in R3. But of course, the idea is that if it's in R3, then we won't be able to write in standard form to begin with. Now, one of the reasons why I want you to write them in standard form because the following. If you write them in standard form, you found it's actually very easy to compare them. The reason why, because if you remember what I told you about parametric form, is that parametric form is not unique. So meaning it's entirely possible that these two parametric representations represent the same line. But in standard form, it's very different, because standard form is almost always unique. Okay, if you reduce everything to like the lowest integers form or things like that, you found that your equation is unique for every single line. So therefore, it's very easy to identify. Now, this important concept of rewriting a parametric form into standard form is essential, especially when you talk about planes and on, which we will talk about later on. That parametric form is really complicated to deal with when you have more than one direction vector. So we will probably want to try to figure out what is the standard form of things. But of course, in some cases, it cannot be done. And I've been telling you that you cannot do a line in R3 or higher. And I'll explain to you why that is the case after this example. Or actually, after we talk about plane, then I will explain to you. So let's try to do this first. So let's go and do A first. So how do I rewrite these two things into standard form? Well, simple. The easiest way to do it is to form the perpendicular vector and then just use our formula. So let's say line 1 is this one. Vector x is equal to t negative 2, 1 plus 1, 5. So the direction vector in this case is negative 2, 1. And if I rotate it 90 degrees, just like what I told you to do before, that will become, what is it, negative y x. And now, along with the 0.15, I can now write it in standard form. It would be negative x minus 2y equal to negative 1, negative 2, dot product 1, 5. So if I simply do my math, I will know that it's negative 2, negative x minus 2y equal to negative 1 minus 10. So it becomes negative 11. And I probably just go flip all the sign just to make it look nicer. And so this is my standard form of this equation. Now go ahead and do the second one. And you found that once you do a second one, it's very easy for you to identify that what happened to these two lines. So let's do the second one. So second will be t, what is it, 4, negative 2 plus 7, 4. So once again, we'll take the direction vector and rotate it 90 degrees. Oops. And that become 2, 4. And then now I'm going to go and write my equation. It will be 2x plus 4y equal to 2, 4, dot product 7, 4. And when I do that, I have 2x plus 4y equal to 2 times 7 is 14, 4 times 4 is 16, so 14 plus 16 is 30. And therefore, if I reduce it, that will become x plus 2y equal to 15. Now, look at these two equations. I will now be able to identify what happened to these two equations. Number one, these two equations are not the same. They are also not multiple of each other. If they are multiple of each other, they would be the same line. But they're not. So therefore, I know for a fact that the first thing I notice is that these two lines must be distinct. Okay? 2. Notice that both of them have the same exact coefficient in front of x and y. Now, what does that mean? Well, that would imply that they have the same exact perpendicular vector. They both have the perpendicular vector 1, 2. Now, okay, of course, the second equation, the perpendicular vector is 2, 4. But once we reduce the equation, we actually can use 1, 2 as the perpendicular vector. So therefore, they have actually the same perpendicular vector, and therefore meaning that these two must be parallel. And because they're parallel, they cannot be perpendicular. And because they're distinct and parallel, they will not intersect. So that would be your answer right here. Now, you can also definitely tell that two lines are distinct by saying, look at this constant. If that constant are not the same while you have the same exact perpendicular vector, it will have to be two distinct lines. Now, however, if the constant are multiple of each other and in the same multiple as the perpendicular vector, then they would be the same line. Okay? But of course, if that's the case, you might reduce the equation so that you see that they would have the same perpendicular vector but not the same number or same number at the end. Now, before we talk about planes, I do want to talk about this first. Why is standard form of a line or the equation y equals mx plus b form of a line or the equation of a line in general unique to R2 but not higher dimension? And the idea is actually pretty simple. Whatever equation that you have, whether it's y equals mx plus b form or the point slope form y minus y1 equal to mx minus x1 form, they can both be rewritten into the standard form. So technically they're all kind of the same thing and they're all equation of the line, but just in different format. And the problem is the following. The standard form of line require a perpendicular vector to right. You have to have the perpendicular vector because the perpendicular vector identifies the coefficients for your standard form, the coefficients for x and y, and also the number c that is equal to by using the dot product of the perpendicular vector and any point on the line. So therefore, having the perpendicular vector is essential in writing the standard form. So now why does it not work in R3 or higher? Well, the problem is because on R2, every line would have a unique perpendicular direction. Okay? Every line. So imagine the following. Imagine you take the pen or pencil that you have and lay it on the table. And now if you take up a second pen or pencil, and you also have to lay it on the same table with the first pen that you put down, but perpendicular to it. You find out that your second pencil will have to be in a specific direction. Now, granted, you can put that pencil either on top or on the bottom of your pencil, but it still only be one direction, meaning the following. Imagine that I draw a line in R2. So here's my line. Then there is a unique perpendicular direction. This perpendicular direction is unique. Yes, it could be go the bottom direction, but that would be just the opposite of this one. So it's not different, but just multiple of this one, which basically counts as the same direction. That's in R2. The problem is in dimension higher than R2, in R3 or higher. A line does not, I repeat, does not have a unique perpendicular direction. That is the problem. That's the reason why we cannot write a line in R3 or higher in regular equation form, because that actually requires a perpendicular direction to exist. And yes, a line have a lot of perpendicular direction in R3 or higher. Okay? As a matter of fact, the easiest way to actually see that is if you take two pen or pencil and just form a T, then that will represent two perpendicular lines. But then you can then rotate this entire picture all around. And you find out that a line actually have a complete 360 rotation of perpendicular direction from it. So that's the reason why it doesn't work. That's the reason why you cannot form a line in R3 or higher using standard form or equation form, because it requires a unique perpendicular direction, and a line in R3 or higher does not have a unique perpendicular direction. It have infinitely many perpendicular directions. One of the reasons why in R3 or higher is easier to represent it in parametric form, because you have a single unique direction of the line that we can use to define this line. Now, with that being said, then what's the deal with plane? Well, here's what happened. Next thing we want to talk about would be this. How about the standard form of a plane? We actually haven't talked about equation of a plane in any way yet. Okay? And the reason why, because you don't have the knowledge needed to do that yet, but now you do. Okay? So first of all, let's review. We call that the parametric representation of a plane is given by this formula. Vector x equal to t1, vector u1 plus t2 vector u2 plus vector t. In this expression right here, vector u1 and u2 are basically two directions vector of the plane, and vector v is any one point on the plane. Now, we talk about how this expression actually come about with basically two intersecting lines. The first line you can think of as t1 vector u1 plus v, and then the second line is t2 vector u2 plus v. And so if you have two intersecting lines, then you would be able to define a plane. But also want you to understand how this expression works. So show you a little picture to illustrate this. So suppose I have this plane right here. Now once again, I'm trying to draw a plane with boundary, but do realize that a plane actually doesn't have any boundary. But I'm just simply trying to draw the boundary so that you can actually visualize the plane. So let's say, imagine this is my plane. And let's say here's my origin. So let's say I want to define this one point right here, which is vector x. So the question is, how do I identify this one point in space, in this space on this plane? Well, let's consider what's given first. So let's say in this case we are given the plane, so that therefore we know two direction vector, u1 and u2. And we're also given a position vector, v, on the plane. So how do I actually describe this one point x in this picture? Well, this is how. First, I'm going to identify point v on the plane. So this is my position vector that allow me to travel from the origin onto the plane where x is. Then next, I do have these two directions that I'm allowed to go. One of them is probably vector u1, and maybe the other one is vector u2. Well, the problem is these two vectors might not be long enough for me to get to x. So what do? Well, simple. We do the following. We multiply u2 by some scalar t2 to stretch out the direction vector. And then we do the same thing with u1 by multiplying u1 by some vector t1 to give it the right length. And then add them up tail to head to actually travel to where point x is. Which is the reason why the parametric representation is this. Is to define point x, I have to take the direction vector that gets stretched out by t1 plus the direction vector u2 that gets stretched out by t2, and then also add the position vector v to get to where I have to go. So this vector right here actually describes the sum of this red one and these two green ones together to define this one point, which basically give you this vector. That is vector x. The sum of these three vectors together. That's how they work. Good so far? Now, the interesting thing about it is the following. On this definition, it can take any one line, any one point on the plane to define this parametric representation. So there are definitely many variations, and it will only require two different direction vector to do that. Now, however, if you think about it, on any given point, like let's say take a point v for instance, is vector u1 and u2 the only two directions that you're allowed to go? Well, the answer is no. As a matter of fact, if you pick any single point on a plane, you find out that a plane actually have infinite number of directions. So if you picture you have a plane, and you also define a point on this plane, how many different directions can you actually travel on this plane? Well, you can travel this way, maybe this way, maybe this way, 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 this way. And as a matter of fact, on any given point on a plane, there are actually infinitely many different direction vector. There are infinitely many directions that you can go. The interesting thing about it is that to define a parametric representation of a plane, you only require you to find two different directions. And those two directions just cannot be like opposite direction or the same direction. Then you'll be able to define a plane. And it is because of that lead to the fact that we can have infinitely many different parametric representation. Because I can find any two directions that I liked and any one point on this plane. There are infinitely many points to choose from. There are infinitely many pairs of direction to choose from. That's why parametric representation have infinitely many variation. And which also become a major issue is that potentially everyone can be described the same plane, but just using different directions and different points. A better way to actually describe a plane from that aspect is to avoid the confusion of having many different definitions, is to figure out a way to actually define a plane in more a unified way so that everyone have the same answer. And that is the purpose of the standard form of a plane. Just like with lines, parametric representation can be very different, but then once you form it into a standard form, it becomes pretty unique. And you'll be able to identify quite easily whether the lines are the same or different. And you can also identify perpendicular and solving for intersections and things like that. All that become a lot easier to do. The only problem is that only in some dimension you can do that. For a plane, you will be able to form the standard form of a plane in R3, but R3 only. Okay, so show you how that works. Okay, so first of all, what you have to do to understand is that the standard form of a plane exists only in R3. Now, interesting thing to note is that mirror what we know. Notice that a plane is a two-dimensional object. How do I know it's two-dimensional? The parametric representation has two directions and two perimeters. That's how I know. Remember I told you that in parametric form, the number of perimeters usually define the dimension of the object. And then what dimension the vectors are in determine the dimension of the object of which the object exists in. So in this case, a plane only exists in standard form in R3. Mirror, standard form of a line, only exists in R2. Well, how? Because a line is one-dimensional and it only have a standard form in R2. A plane is two-dimensional and only have a standard form in R3. And if you follow that direction, you probably can guess if we have something that's three-dimensional that is similar to a line or plane, then it will only exist in standard form in R4. And you're correct. But those things we'll go talk more about it in chapter 2. So right now let's focus on just planes and lines like the way you know it. So the way to generate the standard form of a plane is to do the following. To generate the standard form of a plane in R3, we need two things. Number one, we need the perpendicular vector of the plane and any one point on the plane. Now, hopefully some of you have a little bit of deja vu, because those are the two exact same thing we need to generate a line in R2 by standard form. Is that coincidence? It's not. Because from a geometrical standpoint, a line in R2 is actually the same as a plane in R3. And I'll explain more of this concept later on. Now, then how do I actually form this standard form of a plane? Well, we actually use similar concept as before. Imagine that I have this plane. Here's my plane. The problem is exactly the same. Let's say I have this one point right here, which is called vector x. I'm going to have to try to find a way to describe what this one point is. Just like what we did here. I need to find a way to mathematically allow me to identify this one point that's on the plane. So how? Well, let's start with what we are given. Let's say we are given the perpendicular vector, which is vector p. And let's say we're also given a point on the line, a point on the plane. Vector x sub 0. So now let's start with the following. Let's say here would be where vector x sub 0 is. And of course, we're treating vector x sub 0 to definitely not be x. X can be any point. X sub 0 has to be a specific point that I choose. So I'm going to choose this point right here. Perpendicular vector, here's an interesting thing. Every plane has a unique perpendicular vector in R3. As a matter of fact, if you look at the piece of paper that's on your desk, if I ask you to take your pencil and put it so that it's perpendicular to that piece of paper, there's only one way to do it, and is to put that pen, put your pen straight up off the plane, like this. Perpendicular vector. So now, then how do I describe this point using this perpendicular vector and this point x sub 0? Well, guess what? We do the same thing like we did before. What I'm going to do is, I'm going to now define the direction vector that go between x and x sub 0. This vector would definitely be on the plane because both of its endpoints are on the plane. So therefore imply that this must form a right angle. Now hopefully some of you see where I'm going with this. And if these two vectors, vector p and vector x minus x sub 0, form a right angle, then I can now define the following. Because they form a right angle, the dot product must equal to 0. Now, I know some of you might be saying, oh my god, isn't that the same equation we did for line? Well, let's check. Whoa, it is the same equation for line. How does that work? As with a lot of things that we learned so far, an equation is an equation is an equation. But what dimension that equation is in is dictated by the vectors that we use. Just like the parametric representation of a line is exactly the same whether it's in R2 or R12 or R2020. It is the vector that defines the dimension is in, not the equation. That's how it works here. This equation happened to be the same equation as line. As I told you, a plane is actually, from a geometrical standpoint, is exactly the same as a line, but just in different dimension. So now how does this equation work? Well, I'll show you. So this is the last thing I want to show you because the video is already 33 minutes. So this is the last thing I want to show you. Vector P, in this case, I'm going to call it ABC. Notice it's now in R3. Let's say vector x sub 0 is now x sub 0, y sub 0, z sub 0. And let's say vector x in this case is our variable vector, which would just be x, y, z. Then now I can basically do this dot product just like what we did before. ABC dot product x, y, z minus x sub 0, y sub 0, z sub 0. Oops. Okay, let me see if I can do this. Oh, yep, there you go. Equal to 0. Now, if you go through your math, you find out that there will be A, B, C, dot product. I'm sorry. Dot product. X minus x sub 0, y minus y sub 0, c minus c sub 0 equal to 0. Yes, you're probably having deja vu because we can't do the exact same thing with line, except that we don't have c and z. And now if I do the dot product, it would be, and I'm going to distribute, it would be ax minus ax sub 0 plus by minus by sub 0 plus cz minus cz sub 0 equal to 0. And then now what I'm going to do is I'm going to just keep the xyz on one side and move all the one with the x sub 0, y sub 0, and c sub 0 to the other side. And what I'm going to do is I'm going to call this the constant d. And now what I have is a standard form of a plane. Notice the standard form of a plane mirror the standard form of a line. A, B, C, the coefficient for x, y, and z are the perpendicular vector. And then the constant d is the dot product between any one point on the plane with the perpendicular vector. Both of that are exactly the same, mirror exactly the same thing as line. All right, unfortunately, I'm going to have to stop right here. The video is already too long. So we'll continue this discussion tomorrow or on our next video. Okay, bye-bye.